Welcome to Almost Here, Round the Corner Future Technology podcasts with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Coming to Dallas, Texas, September 14th, 15th, and 16th, 2018, the Blockchain and Future Tech Expo. This is going to be a gigantic conference of over 5,000 people. We're going to be talking about blockchain and its applications. We're going to be talking about quantum computing, cybersecurity, artificial intelligence, and several other future technologies that are poised to and actually changing our lives as we speak. Here's why you should attend. As you may know, early adopters are the ones that investigated and profited from things like the gold rush in the 1800s, from the dot-com boom in the 1990s, from the internet boom in 2005, from the smartphone explosion in 2007, from the real estate boom that ended in 2008, and of course, from the Bitcoin boom that started in 2012. Early adopters act now. They don't wait till later. They go out west first. In their covered wagons, they find the biggest gold nuggets. If you consider yourself an early adopter and you want to find the biggest nuggets, then you owe it to yourself to attend this upcoming conference. Blockchain is going to affect how we control and store our medical data, how we send money around the world, how we bank, and more. But artificial intelligence, quantum computing, and cybersecurity will play a pivotal role in our lives as well. And that's why our next event, September 14th to the 16th at the Dallas Convention Center, is going to have not only 5,000 plus attendees, but will showcase blockchain, AI, cybersecurity, quantum computing, and more. You want to get in on the coming gold rush of future tech and opportunity as an early adopter. Don't be left out. To register, go to bftexpo.com. That's blockchainfuturetechexpo.com. Thank you.
Hello, this is Richard Jacobs with the Future Tech Podcast. My guest today is Michael Laskey. He's a PhD student, about to get his PhD, hopefully, at the University of Berkeley, and he's working on some robotics-related research. So, Mike, how you doing?
Doing pretty good, man. Doing good.
Yeah. Well, can you just give a little background on yourself, and then tell me about the research that you're working on? What's your PhD about?
Okay, yeah. So, I'm a fifth-year PhD student at UC Berkeley. I came out here by Michigan, where I did my undergrad, grew up in. And when I started my PhD, it was actually right around the time that deep learning made very promising results on ImageNet. So it was about 2013. And a lot of my PhD has been looking at, well, how do we take these deep learning results and apply them to robotic manipulation? Manipulation's always been very challenging. It's one of the hardest things for a robot to do is actually manipulate the physical world. And you can see that because we don't really have that many manipulation products out there right now in terms of robotics. So
why is it so hard for a robot to manipulate stuff? Does it tend to crush things or just not be able to grasp them with the right pressure, or what are the problems it has?
Yeah, so it's a pretty hard problem because it kind of couples perception of the world. You have to really understand everything around you, and also physics, where we don't always have good contact models for how things behave under pressure. So it's easier potentially to plan the motion of a robot in empty space, and then the self-driving car could be. It's easier to control just where a car moves in empty space versus actually me interacting with objects and trying to get them in the right pose. Just because the models of the world we have are limited.
Okay, well, we'll keep going. So you're working on that, and what else?
So one of the ways that deep learning can be applied to robotic manipulation was this idea of imitation learning. In imitation learning, basically, you have some supervisor that could be a human that could show the robot how to do the task. So what's nice about that is humans are really good at manipulation, probably one of the best creatures on the planet at it. And by having them show the robot to do, the robot could potentially learn how to just mimic this behavior or kind of generalize that behavior of the motion. And how it works is a human would perform the task and a robot would treat it like a supervised learning problem, where every state the human visits would be the input, and then every action the human applied would be the control signal. And you would try and learn a mapping between input and control, similar to how we would learn in image classification, a map between image and class label, such as a dog or a cat. So that's kind of where I started my work, was thinking a lot about this problem and how do we build systems to collect data. So does a human provide feedback in sort of teleoperation or remote point and click interfaces? And also, what are the best ways to get demonstrations? Should we just have the human like passively teleoperate or provide more of a interactive kind of experience with the robot?
Well, once a robot watches someone do something, you would think you'd be able to observe how its algorithms change, and then maybe you'd be able to capture that for future robots, wouldn't you? Or is it just a one-to-one correspondence, and once the robot, quote-unquote, learns, that's it? It's a black box?
Yeah, it depends on how you kind of build the system. That's some of the nuances that you definitely encounter applying these algorithms. So ideally, you'd like it to be more than just a black box where the robot can like learn some more high-level information and transfer it to other robots. But you could also design the system to be very specific to that robot, where you say, I want this one robot to kind of overfit to this one environment it's in. So a lot of times how people kind of model the problem is either one of those spectrums. So some people have more of a black box approach. I'll get in some like VR setup and then teleoperate the robot exactly, and then try to learn just that behavior. Or I might do more high level control, and then the robot would learn more like high level goal states or grasp plans to go to, and then its low level like robot specific control would take over to enact those trajectories.
I have kind of a basic question. I've been hearing about deep learning, and it seems like a really recent breakthrough in AI. What is it compared to machine learning, or why is it a recent breakthrough? What does it do?
Okay, yeah, that's a good question. So commonly it's a type of machine learning, so that's definitely not like one or the other. What's interesting about more traditional machine learning is a lot of times when we would do it, we would have to first extract features from our data. So we would look at our data, which could potentially be high dimensional, like an image, and then extract certain features to reduce the dimensionality of the problem and make learning easier, and then try and get some invariance in those features. Deep learning takes the approach of, well, I'm just going to learn both the features that I want to extract and also the classification jointly, or the regression jointly. So here you're actually kind of learning an end-to-end style, both feature extraction to reduce the dimensionality of the problem and also to predict. People have a lot of like really kind of interesting theories on this, is like from an information perspective, how you're kind of like learning to reduce the size of the problem and then also jointly predict. And now I think why we're starting to see this actually come into play now, and like why it actually is starting to really work well, is because we have a lot bigger data sets, and we also have a lot more compute available. This is a very computationally expensive kind of algorithm to do this joint learning, and with recent advances in GPUs, we actually can do that efficiently. Also, you can potentially overfit a lot. So if you don't have a big data set, it could actually be very prone to error because it might learn features that are way too specific to your small data sets. So those are kind of the trends: is bigger data, faster compute. But the cool thing about it is once you learn these features, they can transfer. So we did experiments with our robots on much smaller data sets using pre-trained features, and can actually get really cool performance coming out of that.
So deep learning sounds like truly unsupervised learning. Is that a fair way to characterize it?
Well, you need supervision. So it's it's not unsupervised because you are feeding it labeled data sets. However, it's basically learning more about the representation of the domain than traditional supervised learning, which would use handcrafted features.
So what are the number one things that you want to accomplish with your PhD research? What activities would be most beneficial for a machine or a robot to learn? To grasp things, to carry things?
Yeah, I think the task that I'm most excited about these days, and we just built a prototype, is mobile decluttering. So in that task, you have a robot on a mobile base. So we have a robot in the lab. It's like a Roomba, but it has an arm on it, and it has to go around the room and actually pick things up and put them in the right spot. That's really cool because it's unstructured, so you have to be able to navigate in an environment where you don't have an exact map or exact knowledge where everything is. You have to detect items, and you have to also think about the goal state a lot, like where should the different items in the house go. I think this task is cool. It applies to kind of like cleaning up a home, cleaning up areas, and also the technology needs to make it could be used for a lot of other types of robotic tasks. So really just think about this mobile decluttering is definitely the thing I'm most excited about right now.
That sounds like a really tough task because would the robot sit there first and scan the whole room so it knows not to bump into stuff and look at like 30 different objects and then decide the order to best do it in? Or is it just start with one and kind of goes from there and observes as it goes?
Yeah, it's definitely a tough task. I don't think we're close to it yet. The way that we model it is basically the robot would enter a room and then just try to navigate around, not collide anything, just move forward without collisions. And then when it sees an object that it would detect out of place, it would then plan a motion for it and then try to put it somewhere else.
So how far have you gotten? Have you had a robot you programmed do this? Go into a room and like put couch cushions back on the couch or put dishes away, or what has it done?
Well, so the robot we have, this is a task that we just started on. So right now we've gotten it to basically, if you put a pile of objects on the floor, it can go through and start separating them by doing push motions. And once it finds one it wants, it can put it into a bin. So we can work with about 4 objects right now, 4 object categories, and they're kind of tools from like a machine shop. So the idea here would be decluttering in a machine shop.
That's pretty cool. So is it working? How far along are you with it?
This is a relatively new project, but after my PhD, I'm going to be continuing a lot of the ideas. So about 2 weeks in, and it works well. What it does though, when it isn't sure what to do, is it actually asks for help. So it can, about 20% of the time right now, it actually asks a human for help. So it's autonomous 80, and then it's kind of teleoperated at a very high level, about 20%. And it can be pretty successful when you have this combination. What we're hoping on doing, though, is trying to learn that other 20% and make it completely autonomous one day.
Well, how is it succeeding and how is it messing up? When does it destroy stuff and then ask for help? Or does it, it's funny, I guess it sounds like it has a personality, Is it cautious?
Yeah.
And it asks for help constantly? Or do you have a setting where it's like, shut up and leave me alone, and it breaks everything and then asks for help?
Yeah, so how we framed asking for help, so we have basically what it considers is how confident it is and what it thinks the object is. So right now, a lot of times when it messes up, it thinks certain objects are other types of objects. For example, it's supposed to put, sometimes it ends up putting screwdrivers in the glue drawer or the glue bin because it thinks screwdrivers look like glue. So when it's unconfident in what it's doing, or when there's a big pile, that's when it starts asking for help because its vision system is starting to fail. And the cool thing is we can actually measure its confidence based on some of the more modern neural network architectures.
So what happens when it asks for help? Its confidence falls below a certain level?
Yeah. So, and we're looking at setting that a little bit more intelligently, but when its confidence below a certain level, it's going to ask for help. And then it queries a remote human on the internet to come in and actually specify where the object is and what class label it is, which it can then use to help plan its grasping.
So do you find that it can get caught in, in a rat hole where you help it and then it needs more help and more help and more help? Or once you help it, it's back to its operation and it keeps going and it's successful? Are there things that can happen that can throw it off track where it keeps going off track and can't seem to right itself?
Yeah, no, definitely right now with robotics, there's always going to be situations where it can just really fail forever. But most of the time you can help it and then it's going to go and actually keep doing the task until it encounters another tough state. But it's very possible right now with this technology, you can provide help and they can not understand that and go off. So into kind of a rabbit hole there. But it doesn't happen at all.
It'd be funny if you had a guilt feature where it starts complaining and says, I can't do this. Can't you do this? And help me.
Yeah. Yeah, it'd be interesting to kind of punish it more for asking for help so many times.
Well, or it'd be interesting if you could give it somewhat of a, do you have a feature where like you said, the confidence will fall below a certain level and it just will ask for help, but can you program it where you have a feature where it'll try it anyway and then learn from what it's doing? Like
a very confident robot that doesn't ask for help very much, or one that asks for help all the time and is very cautious?
Yeah, no, that's a really good insight. What we want to do too is let it kind of explore this sort of confidence value. So even when it thinks it's not always sure, it's still try out an action and then feel penalty from that. And by trying to kind of optimize this, maybe we can find a better threshold of when it actually is sure or not. So really, what we want to do is be able to balance sort of like exploration, so the robot is able to take new decisions and try different things out and figure out where that right balance is.
What would be the goal of punishing it, though? I mean, it's not human. It's not going to like cry or say please or any of that stuff.
So with the punishing it would be like giving it negative reward. So right now we measure its performance based on how many times it asked for help and how successful it was. So we don't want it to ask for help too many times because that's going to require like a human resource. So we want to so we try and make it like optimize the sort of reward value of how successful it is and how many times it asks for help.
So what kind of application would it be used in if once it's successful? I mean, what are the commercial applications that, you know, maybe you've been asked, hey, if you could make this work for XYZ, we'd love it.
Yeah, so the task that it's really going after is just you can think of it in applications such as the one that we're targeting right now is like decluttering machine shop. So it could come in after people have been working in some like machine shop for a while and clean it up at night. And then you could have a sort of remote call center for those corner cases to actually help assist the robot. Another application I'm excited about is assistive robotics. So how could the robot go into a home and actually declutter the home environment to just make things tidier and extend sort of independence in living. And so I think, yeah, like anytime where you have like objects on the floor and you want to pick them up, that's sort of the applications that you'd be considered. You could also extend it potentially to like stacking grocery shelves and applications such as that, order fulfillment, where you have to basically pick up items, put them on shelves, take items off shelf, and move them around.
So this sounds like it combines a lot. It needs computer vision. It needs, like haptic feedback and grasping. I mean, it seems like it requires a ton of skills in order for it to work.
Yeah, no, and that's really why robotics are very challenging, is because they're complex systems with a lot of different components. And
what did I leave out? What is it? It needs machine vision. It needs I don't know what you call the grasping, but what are the elements it needs in your mind to make it work?
So it needs like really strong machine vision, the ability to enter a room and really do semantic scene understanding, grasp planning. So thinking about how do I manipulate objects, how do I engage them in a grasp to visually contact myself, visually fix them to their body. The ability to build a map is also you have to have some sort of map of where the room is. You need some way to actually do navigation and movement on potentially terrain such as carpet, which can be hard for localization purposes. So you have to have some base that can actually move around the room and understand where it is. And that could require, like our current robot has a LiDAR-based sensor on its base. So you have to think about LiDAR fusion. So in some sense, you kind of need a lot of the technology of a self-driving car, but then on top of that, a lot of the manipulation technology. So it really builds on a lot of recent work in self-driving cars as well.
So the LiDAR maps the room? Is that what it's used for?
Yeah, right now it maps the room in terms of obstacles, and then it also is used to help localize the robot. So when the robot moves forward, it kind of sees how far did these features change, and then that allows it to know how far did it move in space.
Does it have to rescan the room at a certain frequency? If it picks up an object, now the room's different. And as it moves through the room, now its place in the room is different. So how often does it have to rescan the room once it initially does it?
Yeah, our LiDAR, I think, scans at a rate about 30 hertz. And we have a separate thread actually processing it and then doing these more low-level calculations. What's interesting is you have a lot of different processes going on, interacting with each other on these mobile robots.
So when you see it ask for help and fail, what's failing? What's the weakest component of it? Is it the machine vision? It's got to look at all these different kinds of objects, or is it, what goes wrong when it goes wrong?
Yeah, so the biggest component right now, I would say, is the ability to detect objects in space, the machine vision side. And why that is because we only trained machine vision algorithm about 200 labeled data points. So naturally, it's going to just have some error because we didn't have much data. As we scale that up to larger data sets, we might actually see that work better. But while computer vision has made great progress, when you take these object detection networks off the data sets they were trained on, you have to retrain them locally to your data sets, to new instances, and you might not have that much data. So still that retraining step needs a lot of research on how to make that more reliable. The other thing that can go wrong sometimes is precision of the grasps. So our robot has about 2 centimeters of error, or I think 1 centimeter of error. So thinking about grasp robustness is really important. How do I plan grasps so they're robust to that kind of error? So these are kind of the things that we still are thinking about a lot. But so really just object detection and then having robust grasps. So that's some of the challenges that we face. However, if you scale this up to more complex domains where you have different like texture in your carpet and stuff, there could be other problems with localization and just motion planning on that.
Well, if you said the grasp differential is what, 1 centimeter or 2 centimeters?
It's about 1 centimeter, the error in the grasp planning.
Well, how much of a force differential does that make with that much of a difference?
Well, it's really it could be the difference between your hand actually grasping the object in the center or actually missing the object. We've been doing experiments trying to grasp Legos, and if you don't approach them in the right direction, you can actually miss the object.
What about crushing stuff?
Crushing stuff hasn't been too much of an issue. I think our robots don't grasp things that hard. We have more compliant robots that are human safe. But if you get to like an industrial robot, you might have to worry about that a bit more.
All right, so they don't have a problem crushing stuff, but they can miss things. And can you tighten it up so it's less than 1 centimeter, or is that really not necessary? Is that enough tolerance?
So I think it really depends on the objects you're manipulating. For a lot of home objects, such as the bottles and kind of the things you would naturally throw away, with a wide enough gripper, you might be okay with that kind of error. But you can definitely tighten it up by really exploring the precision in its joints, the precision in its mobile base. The issue is the cost is kind of a big factor. You want these robots to be cheap enough that people can buy them. So there's always this kind of delicate balance between cost and precision.
Well, what about the gripper itself? I mean, does it need to look like a hand? Is it just like a nub that pushes things? Is it like a pincer with 2 paws, or what does it look like?
It actually looks like a pincer. Yeah. It's a 2-claw. It's a parallel jaw gripper, so it has basically 2 parallel plates that would close together on a plane. And a lot of times that's kind of the preferred gripper because it's kind of computationally easy to reason about and plan for. Things like 5-fingered hands are just hard, very high dimensional, and they're hard to do control with. So a lot of times robots would prefer more simple grippers, like parallel jaw.
Oh, so the more fingers, the more degrees of freedom, and it's like a trade-off, I guess, right? If you want more fine control, you need more fingers, but then it gets so much harder to control it.
Yeah, and that's exactly the issue. And for a lot of times, we just want robots to pick things up right away. I mean, that's the first step, and parallel jaws can accomplish that. So it's a really nice trade-off between computationally and what we want robots to just be able to do for the first step. But more advanced things like cooking and really in-hand manipulation obviously are pretty limited, but we might be kind of far off from those tasks right now.
Well, what about if a robot had multiple appendages and they were used for different tasks? You know, some just a bumper would be fine. Some as a pincer. Some you need like, a 3-pronged hand thing.
Oh, yeah. Yeah, I mean, there's actually a postdoc in the lab working on a tool changer for a way to basically have the robot come over and change the tools to different appendages for different tasks. I think deciding when different tools are needed would be a very interesting problem right now in robotics.
Yeah, this is complicated. The more I ask you about it, the more complicated it seems. It's a really hard project you're working on.
Yeah, I mean, robotics is it's very clear vision, but it's very hard to actually really get there. These systems are really complex, and we're just beginning to get prototypes online that can do some of this more unstructured stuff.
Are there any other senses besides vision that would help a robot navigate? I don't know, like the electric field around stuff or the temperature of stuff, or is that not really necessary for the stuff you're working on?
Not for us. I've seen actually a lot of cool work using ultrasound. So to actually basically use almost like sonar sensors for navigation. And then LiDAR is also a really great sensor as well. Also for more outdoors robotics, things like GPS is still a great tool for navigation.
And your robots don't have to go up or down any stairs, right? That would make it probably even much harder, right?
Oh, that would make it a lot harder. Yeah, I'm very fortunate for that. But I think when you look at some of the stuff coming out of Boston Dynamics, there's definitely robots that can do stairs these days. But that's a really interesting place to explore, is like how to have that legged locomotion go up and down stairs. Yeah, well, I've seen they have like a robot that looks like a dog with multiple legs that they try to kick over and it can right itself, and ones that go up and down stairs. But I don't know if it could do any of the things that your robot can do. But I guess do you see this? Again, I guess this is my biggest question: is once a robot learns, how to grasp stuff and how to rearrange tools and clean up a room, how portable is that skill? And will this become like a modular set of libraries of skills that you think in the future people will piece together to make a much more capable robot? Yeah, I think it could definitely be very modular. So a lot of times our software actually operates at the stack of we just assume you can put your gripper in a fixed position, and somebody who's making a mobile base with wheels or a mobile base with legs can also just operate at that API level, so being agnostic to this. So there's definitely potential for a legged robot to be swapped out for the mobile wheelbase that my robot currently has, and vice versa. So I think we're definitely going to see a lot more software coming online, like software libraries and modularity and API design to support this like ecosystem. And that's going to be really exciting to see just a much more interest in software development for robotic systems. Okay, well, very good. So what's going to happen with you from here? You got about a month left, you said, in your PhD, and then where are you moving on to, and what are you going to work on next? Yeah, so I'll be just trying to finish up my thesis, get everything done. There's a few like theoretical problems I'm still trying to figure out. Once I get done, I'll actually be joining the makers of the robot I'm working with now is Toyota. So I'll actually be joining a team there working on similar problems. So I'm very excited about that. And do you know what you're going to be working on, or can you say, or is it proprietary? Yeah, I think at a high level, it's going to be it's thinking about mobile manipulation for assistive home care. There's a big push to really see how far can we take these robots within the next 5-10 years, and doing a lot more kind of scaling up some of the experiments I was talking about. But I think exact details, I don't know if I can really specify too much. Oh, that's fine. That's great. Yeah. All right, Mike. Well, very good. If people want to contact you and ask you about your research or any of that stuff, what's the best way for them to get in touch? Email's the best. So I think you guys have my email address. Well, I can give it to you. Yeah, if you wouldn't mind, just restate it. We can put it in. Okay. So email is the best way to contact. Laskey, MD, Laskey, MD @ berkeley.edu. Okay. All right. Very good. Okay. Well, Mike, I appreciate you being on, and I'm looking forward to a robot cleaning up my room in the future, if I don't have to do it. Yeah, one day. All right. Well, it was nice talking to you, and have a good day. Coming to Dallas, Texas, September 14th, 15th, and 16th, 2018, the Blockchain and Future Tech Expo. This is going to be a gigantic conference of over 5,000 people. We're going to be talking about blockchain and its applications. We're going to be talking about quantum computing, cybersecurity, artificial intelligence, and several other future technologies that are poised to and actually changing our lives as we speak. Here's why you should attend. As you may know, early adopters are the ones that investigated and profited from things like the gold rush in the 1800s, from the dot-com boom in the 1990s, from the internet boom in 2005, from the smartphone explosion in 2007, from the real estate boom that ended in 2008, and of course,
from the Bitcoin boom that started in 2012. Early adopters act now. They don't wait till later. They go out west first. In their covered wagons, they find the biggest gold nuggets. If you consider yourself an early adopter and you want to find the biggest nuggets, then you owe it to yourself to attend this upcoming conference. Blockchain is going to affect how we control and store our medical data, how we send money around the world, how we bank, and more. But artificial intelligence, quantum computing, and cybersecurity will play a pivotal role in our lives as well. And that's why our next event, September 14th to the 16th at the Dallas Convention Center, is going to have not only 5,000 plus attendees, but will showcase blockchain, AI, cybersecurity, quantum computing, and more. You want to get in on the coming gold rush of future tech and opportunity as an early adopter. Don't be left out. To register, go to bftexpo.com. That's Blockchain Future Tech Expo.com. Thank you.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.